So today I want to look at these practical problems, and in the exam that's coming up in May, you'll be, for the further marks, good, pass, merit, etc., applying the rules of differential calculus to an engineering problem is where you're going to get those marks. So looking at some practical problems, not can you differentiate this function, but more, apply it. And then after that, I want to make a start on looking at some further methods. There are three we need to look at: the product rule, the quotient rule, and the chain rule. We'll probably introduce the product rule today. So that's the aim for today. So we're going to look at some examples. They're in the textbook, so you'll be able to see how they work it out, but we'll go through it ourselves, and then I'll give you some exercise to have a go at and point you at the right sorts of questions. So let's look at the first one. Here it is. And it's on page 423, although you don't need to look at that now, but it's there if you want to look at it. Let's look at it then. Read the question. So the length L in meters of a certain metal rod at temperature theta degrees centigrade is given by this. So L equals, this is the function, 1 plus 0.405 theta plus 0.60 theta squared. That's the function that describes what's going on in this metal as you heat it up, how the length is changing. So this length is dependent on theta, so I could write it as L brackets theta, which is telling me that this is the L function, something that's giving us the change in length, or the length rather of a piece of metal, and how that changes with theta. The 1 comes from the fact that this is going to be the original length of the thing, whatever it was, plus this extra bit of length. So it looks like the temperature is having some sort of linear effect here and a square effect here. We've got to determine the rate of change of length in millimeters per degree centigrade. So what does that tell us? That tells me two things. First of all, it tells me that I've got to differentiate it, because when I differentiate something, that tells me the rate of change. Okay? So the rate of change if I'm after the rate of change, this implies differentiate, because the differential tells us a new function, remember, that tells us the rate of change of the original function, i.e. find, and if we're using this sort of notation, L prime theta, or dL by d theta if you're using the other notation. The other thing this is telling me, as I was reading it, it occurred to me, as soon as I start looking at these things, I'm thinking of units. This is telling me how the length in meters is changing, but I want to determine the rate of change of length in millimeters per degree centigrade. So straight away there's a little bit of an issue around units. So I need to change these to millimeters, which is actually going to help me quite a lot when it comes to the numbers, because they're very awkward numbers, aren't they? And one of the things that comes in engineering is that so far we've been looking at questions where the numbers, 5x squared and small, nice, easy whole numbers. In engineering, it's highly unlikely you're going to get a whole number for a start off, and the answer at the end is going to be a large number of small numbers, so you need engineering notation, stuff like that. And we've got a problem like this here. We've got very, very small numbers. So it helps that we're going to go to millimeters, and we can also possibly even use engineering notation. So how can we rewrite this function converting to millimetres. What have I got to do? Yes, that's right. So I've got to multiply by 1,000 effectively, haven't I? So it's 0.05 theta plus minus 4, I think you mean. Yeah. Theta squared. So, or we can write it like that, and that's better already, isn't it? Now we've got the length in millimetres, because we times by 1,000. So now we need to differentiate. Write down what you think the differential is, L prime theta. Think about the rules of differential calculus, refer to the table if you need to. Write down what you think the differential is. So we get L prime theta equals 0.05 because the 1 disappears and the theta disappears from our table of differentials. And then for the last one, the 2 comes down, times by the number in front, and then take 1 to the power. Woo! So that's our differential function. What does this differential function tell us? The rate of change of the original function with respect to theta. If we put out this function into autograph, which I've done, here it is down here. Let's put it into our notes. So if I plot the function, that tells you the rate of change of length with, so it's L up here, with temperature. Notice for positive temperatures, the length is just increasing. Now the model is implying that for negative temperatures, something weird happens around here. It looks like it goes to a minimum value, for the length goes negative, okay? So in other words, this couldn't possibly happen. And so we're only interested in this model from 0 onwards. And it's telling me from 0 onwards, the length is increasing, okay?
So what's that?
That's just, this is the mathematical model that's describing this. So this has no bearing in the real world, okay? And that often happens in engineering. The mathematical model is something we have to understand from the situation and say, well, this part of the function is not actually relevant in this situation, okay? So there's our model, and it's telling us the rate of change of the function. So if we go back to the question, we've now got a function that would tell us the rate of change in millimeters per degree centigrade. The rate of change, which we might be interested in if you think about it, it's increasing at this number of millimeters per degree centigrade. So what is the rate of change of length when the temperature is 100 degrees centigrade? So for part A, we've now got our differential function. So the rate of change of length when the temperature is 100 degrees centigrade would be how we might write it. That's our differential function, L prime, when theta equals 0. So that equals 0.05 plus 0.308 times 100. And we work out what that is. I think I can probably do that without a calculator. Times by 100, 0.08. So 8 plus 5 is 13, 0.13 millimeters per degree centigrade. It's increasing at the rate of 0.13 millimeters every degree, okay? Which might be useful to us as engineers. That's the rate at which it's increasing. If I add 1 degree temperature rise to that piece of metal, the length is going to increase by 0.13 millimeters. Well, yeah, you could do, couldn't you? You could divide by 1,000 and express it as meters per degree centigrade, yeah. But it's probably in millimeters because it's a more convenient number, yeah. What about B? Work out the rate of change of length rather when the temperature is 400, which is what it was for part B if we look back, okay? What's that going to be? .05 plus 0.308 times 400, which turns out to be, is it? Yeah, it won't, because the first bit will be the same, Tom, so it's not quite like that, is it? Millimeters per degree centigrade. So as it gets hotter, look, the rate at which the length is changing is increasing. Look at the answers. Okay, it's increasing at the rate of only 0.13 millimeters per degree centigrade at 100 degrees, but 400 degrees, it's increasing at the rate almost 3 times that, 0.37. Okay. If we look at the function that we plotted, remember we've not got, well, we've got 100 degrees centigrade here, so I could go back to autograph and expand out and see what's going on to 100, but look at the curve here. You can see that the rate is increasing, that the gradient's increasing, Liam. Okay? And so I would expect that the rate of change of length with temperature is going to increase as the temperature increases. And that's borne out in these results here. Okay?